Hi, so today we're going to be doing a Fourier transform, and the Fourier transform we're going to be doing is the Fourier transform of the Gaussian function, which is given by this expression. There are more general Gaussian functions. For example, this exponential would be raised to minus some constant a times x squared, and then here some other constant b multiplying the exponential. But for now, we're just going to keep it simple and work with e to the minus x squared. Okay? And well, aside from the mathematical enthusiasm for Fourier transforms, there is another reason, a physical reason, important reason, and in engineering it's actually also really important, for calculating Fourier transforms, and particularly of this function. So I'm just going to do a quick introduction about why quantum physics needs this, and then we'll just get on with the calculations. So in quantum physics, instead of, imagine we have a particle that's moving in the x-axis, okay, it is moving on the x-axis, it's just moving in one dimension. So usually we'll say, well, its position, if this is the origin, its position here is just x, and it's exactly x, is well defined. Nevertheless, when we go to the quantum world, in quantum physics, we no longer have a well-defined position. Instead, we use what's called a wave function, which is denoted by c, of xt in this case, which if we take the modulus and we square it, well, then this gives us the probability of finding a particle at a position x. Of course, if we integrate, right, this wave function squared from a to b, this gives us the probability of finding a particle on the interval ab. And well, what does the Fourier transform have to say here? Well, it's also really useful, instead of just the position, to know the momentum. And to find the momentum, we have an analogous wave function, which we will denote by a lowercase c. And in this case, instead of x, we have a p, and it also depends on time. To find this function, we just take the Fourier transform, which I'm going to denote by this calligraphic f. So we take the Fourier transform of this function, this wave function, and we get another wave function, which, if we take the modulus squared, gives us, again, the probability of a particle having some momentum p. Okay, we're no longer talking about position, but momentum. Likewise, if we have this function, we take the inverse Fourier transform, denoted by this, and we get our regular wave function in the position representation. That's what it's called. And this one is the wave function in the momentum representation. So that's why it's important to kind of want to do the Fourier transforms. And in particular, the function e to the minus x squared, well, it's related to what's called a minimum wave packet. It's not exactly given by e to the minus x squared, but as I said, with some constants multiplying, but I'm not going to get into that now. So what a minimum wave packet does is, just a minute, is that, well, the usually well-known Heisenberg's uncertainty principle, which is given by this expression, right? The uncertainty in x times the uncertainty in the momentum is greater or equal than Planck's constant over 2 pi over 2. Okay, as h bar is just h over 2 pi. Well, the minimum wave packet is a, well, it's a kind of wave function such that instead of this we get the equality. Okay, this is what we get with the minimum wave packet, right? Minimum wave packet. Okay, so that's why it's important. It gives us the lower uncertainty possible. So that's why it's interesting to know how to take Fourier transforms of these kind of functions and everything. Well, right now we're just gonna go and calculate it. But before, let me just remind you that the formula or the expression of a Fourier transform is a Fourier transform of f of x, right? This is the notation I'm going to use for the Fourier transform of a function. It becomes a function of p, and it is defined as, well, 1 over the square root of 2 pi times the integral from minus infinity to positive infinity of our original function times this exponential right here, e to the minus I px dx. We're integrating with respect to x. Notice that if we integrate with respect to x, we get a function of p. As I said, the Fourier transform takes a function, the x world, and takes it into I just call this p, into the p world. In this case, x is position and p is momentum. But you could also say f is time, f is a function of time, and we get a function in the frequency domain. But that's just notation and physical interpretations. What we care is that we get a function in some domain and we get into another domain. That's more useful to work with. Now, just a quick mention, actually you can define the Fourier transform in many ways. You can actually just get rid of this and just get this integral, or even include another normalization constant, that's what it's called, by using here h bar. In quantum physics, it's really useful to use 1 over the square root of 2 pi times h bar. This is just so we can get easier results and, well, everything works fine. But it's not too relevant from the mathematical point of view. Okay, so let me just express this. Okay. Now, there's also another way of defining it, that is, instead of putting a minus here, putting a plus. In that case, the inverse Fourier transform will have a different form, but let me just explain it real quick. F of p, this becomes a function in x, and well, let's just say that we, let's just write this here again. Square root of pi integral from minus infinity to positive infinity of my function on p, and here, if we use the definition that I said with a minus here we will have a plus ipx dp. In this case, we integrate with respect to p. It's not relevant for the video, okay? You can skip this part. It's just some introduction of Fourier transforms and some interesting comments about it. So, if we have minus here, in the inverse Fourier transform, we need to have a plus here. But if we define it with a plus here, well, we will just have to write a minus here. And everything is just the same, but well, with these things to have into account. And notice that the inverse Fourier transform integrates with respect to p, getting us a function on x. Okay? So, let's just do it and go back to our regular definition of the Fourier transform. Now, wait, let me just... Okay. So how do we proceed? The Fourier transform of e to the negative x squared to minus x squared. Well, the thing is that there's a common way of proceeding with this kind of integrals, and it is, well, let me just rewrite this. Well, we get our integral from minus infinity to positive infinity, and well, we can use properties of exponentials and add the two exponents, x squared plus I px dx. What we do in these cases is we complete the square. That is, we want this to be a perfect square. We want it to be in the form a plus b squared. Why? Because it's really useful to work with it that way, and we'll see why. So how are we going to do this? Well, let's just write the exponent, x squared plus I px. And, well, okay, a regular square, perfect square, is given by, well, a squared, right, plus 2ab plus b squared. Notice that here we have something squared. Okay, so we can say that x is a, right, because, let me just write this here, we have x squared, okay, plus something we don't know. The next term should be 2ab. Well, we have something, we have multiplication, and we have that this is a. So we have our a, which is x, but we need a 2 here. How do we get a 2 here? Well, we just multiply by 2 and divide everything by 2. And I'm going to write it a bit better now. So 2ip x over 2. Notice this is just the same as that expression, but we have multiplied by 2 and divided by 2. So what we get now here is 2 times ip x over 2. Notice, this is a 2 here, okay. A is x, so this means that this has got to be b. So let's just write this here. I pi over 2. Okay, so far so good. Now, of course, this is not equal to this because we still need to add this term. So let's just add it. I squared is -1, so we get minus p squared over 4. And well, okay, that this is a correct expression. Okay, x plus ip over 2 gives us this expression right here. We have these first two terms. We need this term. So what do? Well, we can just put it in there by brute force, right? Just put minus p squared over 4, and now we get our perfect square. But this expression is not the same as this. We have this extra term. So we can just get rid of that term again by adding this here. Okay, so notice this is 0, 2 over 2 is 1, so we get x squared plus ipx is just the same as this. And using this identity that we have derived, we can actually express this as, well, this is our perfect square. So it's just x plus I p over 2 squared plus p squared over 4. So this exponent can be rewritten like this. And let's just write that down there, or up. So the integral from really add the integral there, minus infinity to positive infinity of e to the minus, well, x plus I p over 2 squared, x plus I p over 2 squared, plus p squared over 4 dx. Using, again, the property of exponentials, right? A to the I plus b is the same as e to the to the b. We can split this into two exponentials. We will just get e to the minus x plus I p over 2 times e to the minus, remember, we shift the minus sign, p squared over 4 dx. And I'm going to erase this for now, okay? So, notice, this is a 4, okay? We are integrating with respect to x. This term right here has no x's there, so it can be treated as a constant, and it can go out of the integral. And so we end up with this expression right here. 2 pi e to the minus p squared over 4 times my integral from minus infinity to positive infinity of e to the minus x plus I p over 2 squared dx. I hope that you can see it well, but okay. So that's what we get there. So all we have to do is to compute this integral. And you could say, yeah, that's right. You could say, well, this integral is just really easy. We can just say that, make a change of variable here, say that u equals to x plus I p over 2, du equals to dx. So this is just the integral from minus infinity to positive infinity of e to the minus u squared du. I'm not going to derive it in this video, but this is a really well-known integral, and it's just the square root of pi. You would get the right answer, okay? Spoiler alert, this is the correct answer. But it's not, I mean, it's not, I think, too rigorous, right? Because we have a complex value on the exponent, and so we should go to the complex plane. So, okay, you can do this if you want, you get the correct value, but we're not going to do it that way today. What we are going to do is say, okay, well, if we go to the complex plane, we're going to draw the complex plane here. And well, this is the real part of our complex numbers, and we're going to denote it by x. And this is the imaginary part of our complex numbers, and I'm going to denote it by I. This is the origin. So all real integrals are just a particular case of complex integrals. So a complex integral is an integral over some curve C in the complex plane of function f of z dz. I'm just gonna call this g. I don't know. This is a complex integral. It's an integral over some path C on the complex plane. When we write the integral from a to b f of x dx, we are calculating a real integral. What we are doing is saying that the path is contained on the real numbers. Okay, so this path is just x. Well, let's just parameterize it. This path is just a set of all complex numbers, right? X plus I y, such that x belongs to the interval ab and y is 0. Right? We will be integrating from a to b along this path right here. This will be our integration curve. But in general, we don't have to integrate along the real axis. We can integrate along any curve from the complex plane. And in fact, that is what we are doing in this integral. Let me just explain for a minute. So, if we call I that integral, I will call I the integral from minus infinity to positive infinity of e to the minus x plus I p over 2 squared dx. This is a real integral, but it's also a complex integral with the curve being restricted to this real axis. So we can go the other way around and say that, well, okay, let me just express this a bit better. I cannot write. Okay. So one moment. Let's just say that this is the same as the integral along some path C of my function f of c dc, where now this path I'm gonna say that it is let's just call it C real. Okay, so what we're doing here is, well, okay, this is just a particular case in which the complex numbers, right, z equals x plus iy, are such that x goes from minus infinity to positive infinity, and y is just this one here, p over 2. P over 2. And this is the curve we are actually integrating in the complex plane. So if we plot this curve here, we get that, well, okay, the set of complex numbers such that y is always equal to p over 2. So if this is p over 2, we are moving on this direction, and x goes from minus infinity to positive infinity. So this will be our curve, C real. And I'm going to call this curve, instead of C real, let's just say that it is C1. You see why? Now, okay, so to proceed from here, we're actually going to define some other curves, because we want to use Cauchy's residue theorem. Okay? So let's say that we define instead the interval IR, okay, because this is going to be going the same integral, but going from negative R to positive R of e to the minus x plus I p over 2 squared dx. So here, our new curve, our C1, is no longer going from minus infinity to positive infinity, but rather from negative R to positive R. This is the curve we're integrating with respect to. Now, what we want to do is to close this curve. We want to make a contour. So to make a contour, we can just go really easy, don't get too complicated, and say, okay, this is going to be C2, this is going to be C3, and this is going to be C4. So what we want to do is to integrate. I'm just going to say, make a line here, so we have some more space. Yeah. We want to define a closed contour, and this closed contour, which is the set of all these three curves, these four curves, is going to be called gamma. C1, union C2, union C3, and union C4. Where C1 is just going to be this curve right here. I'm going to, well, I think you can see it well. Okay. So C1 is going to be the set of all complex numbers, x plus I, y, such that, okay, x goes from minus r to r, and the height is always p over 2. So x goes from minus r to r, and y equals to p over 2. Our second curve is going to be the set of all complex numbers x plus I, y, such that x is always r. X is always going to be equal to r. And y is going to go from p over 2 to 0. So p over 2 to 0. Likewise, C3 is actually going to be a real integral. C is equal to x plus I, y, such that x goes from r to minus r, right, from r to minus r, and y is always equal to 0. And lastly, me just, well, I guess you can actually see it well, so I'm just going to see. And C4, well, it's really similar to C2, right? It's just a set of complex numbers such that x is always equal to negative r in this case, and y goes from 0 to r. And that's what we are going to do. So what we want to do now is to integrate along this closed contour. How? Well, let's just say that j is the integral on this closed contour of our function f of z dz, where I will define f of z, just to make notation shorter, as this. Okay? Just notice that if we plug this in here and we say that z, well, is the set of numbers on C1, we actually get this expression right here. So, yes, so that's what we're going to do. And because this is a closed contour, we're going to make a little circle here just to indicate it. And this circle has an orientation, and it is a clockwise orientation, a negative orientation really. So it's going in this direction. So that's the orientation we have for our contour, and it's going to be relevant when we do Cauchy's integral, Cauchy's residue theorem. Well, okay, so let's just keep on going with this. So this integral is the sum of the integral over C1, the integral over C2, C3, C4. The integral over C1 is just this, because C1 is this curve right here. This is the integral over C1, so I'm just going to call this IR. Okay, this is just the integral over C1. Plus the integral over C2 of my function, plus the integral over C3 of my function, plus the integral over C4 of my function, dc. So we're actually going to start evaluating this integral right here, because it's really easy. Well, easy. It goes to 0. Okay, it's polar again. It goes to 0, and you want to see why it goes to 0. So let's just say that this is called m, this integral over C2 of e to the minus c squared dc. And while using our parameterization of C2, we see that, well, okay, this is just x plus iy. Let me just write this here. E to the minus x plus iy, where x varies, x is always constant, is r, and y varies from p over 2 to 0. So this is just plus y. How do we evaluate this integral? Well, first of all, let's just say that okay, we can just rewrite this limit as minus from 0 to p over 2 of e expanding the square of r plus 2y r y plus I squared is negative 1, so minus really I squared dx. Sorry, dy. I'm so sorry for that. dy. But again, we have the same problem that we had here. We have a complex number, so how do we proceed from here? Well, what we're going to do is to take the modulus of this integral. So if we take the modulus of m, remember m is this, so it's the modulus of this, we get that, well, this minus sign, the modulus of a negative sign is just 1. We get that this is the modulus of that integral. Okay, I'm just going to write it, of 0 p over 2 e to the minus r squared times e to the minus y squared times e to the I times 2ry dy. Why do we write it like this? You're going to see in a minute. Well, we can use a property of the integrals, which says that the absolute value of an integral is lower or equal than the absolute value of the integrand, the inside function. So this is what we would get. The absolute value of e to the minus r squared. Remember, absolute values can be split into terms that are multiplying. E to the minus y squared, the absolute value, and the absolute value, or modulus in this case, of e to the I to ry dy. Now, this is e to the I times some m. Let's just say that m is any real number. This, the modulus of this number is always 1. Always 1. Why? Because this just describes a circumference of radius 1 in the complex plane. Okay, this is a complex plane. And the modulus is the distance from the origin, and it's always going to be 1. So what we get here is that this is 1. Now, an exponential is always positive. So the modulus of this is actually just the same as the function itself, and this is the same as the function itself too. Given the fact now that this does not depend on I, we can take it out of the integral, and we get that this is equal to e to the minus r squared times the integral from 0 to p over 2 of e to the minus y squared dy. How do we proceed now? Well, I want you to notice one thing, and it is that this area, this integral, is finite. It is not infinite. Why? Well, because really what we would get is this. Well, I'm just going to draw it here. You see why it's finite. But of course, you can just pretty much see that it's finite because it has no points where it blows up to infinity or anything. But let's just do it. We are going to the real plane, okay? This is y and this is f of y. If we plot e to the minus y squared, well, at 0 is 1. And if we increase our y, it goes to, let me just see one thing. I think I made a mistake here. Right. Yeah, I'm so sorry for this. This is a negative sign I did not distribute. I'm so sorry. This should be negative and this should be positive. Yes. Minus r squared minus 2ir, and yeah. So sorry for that. And I made a mistake. Do not think about it. It doesn't really change much. Just change that here. This is minus sign, this is a positive sign, and minus sign. Again, I'm sorry for that mistake. But well, okay, so here we have a positive. Again, well, this is just, again, e to the I times some complex real number, so it's just 1. What we get here, well, this is still a positive number, so the absolute value is just the same number. So what we get here is that, well, at 0 is 1, still 1, but if we increase y squared, it actually goes to infinity, it increases, so we can plot this like this. Okay. If we go from 0 to p over 2, this integral is going to give us this area. Okay? Now, this area, if you look at it, is less than the area of this square or this rectangle. This height is going to be e to the p over 2 squared, which is just e to the p squared over 4, and the base of the rectangle is going to be p over 2. So the area, all of this area is bigger than this, and it is finite because it's just this term times this term. You can do it in a more rigorous way by saying that, well, you can just define another function. Let's just say that it is g of y, which would be e to the y squared minus let me just see one thing. E to the p squared over 4 minus e to the negative y squared plus y squared, sorry. Well, from here you will see that this function is continuous because this function is continuous and this function is continuous. And what it would give you is the difference in height at every point. And if you do it in this interval, you will see that it is always positive. And if it is always positive, this means that this term is always bigger than this term, meaning that this function is always bigger than this function, so the area is going to be bigger. But I'm not going to get into that. Just gonna say that, well, this integral is less or equal than, well, just writing this here, e to the minus r squared, than the area of this rectangle, which, well, the area of that rectangle is just p over 2 times e to the p squared over 4. So that's what we have so far. And I'm going to erase this real quick. And okay, so okay, this is curious, but how does it help us? Well, if we take the limit when r goes to positive infinity of this, we see that the limit of this integral, remember again that m is just this integral, the limit when r goes to positive infinity, we get that this is going to 0, right? Because e to the p squared over 4 is going to 0 because, well, this is a negative exponential. E to the minus infinity is going to 0. And this doesn't matter because it's just constant, so it goes to 0. But the definition of a modulus of an absolute value is that it has to be greater or equal than 0. So from here, we get that, well, the limit actually, let me just write it here, we get that the limit when r goes to positive infinity of m is greater or equal to 0, but it is also less or equal to 0. So this can only mean that it is equal to 0. So if we take the limit here when r goes to positive infinity, this is m, this will go to 0 because the only number that has modulus 0 is 0 itself. So from this reasoning, I'm going to erase this. From this reasoning, we see that this is 0 when r goes to positive infinity. Okay, so we are just going to do that. We are going to take the limit when r goes to positive infinity, of all of these integrals. So this goes here, that was said, this said, and this is just the limit. Well, just notice that the limit when this integral goes to positive r goes to positive infinity, sorry, it's just the integral from minus infinity to positive infinity, which is our original desired integral. So instead of writing the limit, we can just write I. Plus the limit of this, which is m when it goes to infinity, is just 0. And now, plus the limit when r goes to positive infinity of my integral over c3, which we get to know what it is, dc And again, well, we're just going to take another limit. When r goes to positive infinity of the integral over c4 f of c dc, or z, however you want to call it. This curve is actually exactly equal to this curve, but on the other side, okay, with negative r. And following the same reasoning, we can actually say that it is 0. I'm going to do it real quick. Instead, we were going to call this n. It's just the integral over c4. Well, c4 is just this. So here, y is going from 0 to p over 2. Sorry, this should be p over 2. It's going from 0 to p over 2 of e to the minus, okay, in this case, x is minus r plus iy squared dy. And well, it's doing exactly the same. What do we get? We get e to the minus r squared times e to the plus 2iry times e to the plus y squared dy. This is exactly the same expression we had before, but with a plus here. Taking the modulus again, this will also go to 1, and we, following the same reasoning, we get that this goes to 0 too. So this is going to 0. Just do it yourself if you don't believe me, but it's exactly the same procedure because we actually have exactly the same integral, except for this term that goes to 1 when we take the modulus. Okay, so far we have this. We have that the limit of this control integral when r goes to infinity, right? When this stretches out to infinity, is just I, original integral, plus the limit of this integral. The limit when r goes to positive infinity of c3. Well, let's just parameterize cc again. c3. Well, c3 is just e to the minus z squared. And what is z in this case? Z is just well, is it c3? Sorry, it's just x. Okay, x varies. All right, plus I y, but y. What is y? Yes, but y is just 0 always, right? Because I need way to retain this integral. So this goes to 0, and we can just write e to the minus x squared dx. And x goes from positive r to negative r. It goes from r to negative r. And well, taking the limit when r goes to positive infinity is just really changing the integration limits. It's just a matter of notation by, sorry, this is positive infinity and negative infinity. And that's what we get. Well, we can just rewrite this as I to the minus integral going from negative infinity to positive infinity of e to the minus x squared dx. And this is our expression. Now, as I said, we are going to use Cauchy's residue theorem. And Cauchy's residue theorem tells us that if we have a closed contour gamma and our function f of z is not analytic in a finite set of points, then this closed integral is the same as, well, let's just write this. Let me just write this real quick. Is equal to 2 pi I times the residue of the function f of z at those set of points, and which I'm going to call Ci. And what is the residue? Well, in this case, we don't actually need to know how to calculate a residue because there are no residues. But I will make some more videos on complex analysis talking more about this. So on our usual initial contour, which is gamma, okay, this is gamma, all of this is gamma, we have that, well, okay, our function f of z, which is e to the minus z squared has no points where it is not analytic. There are no conflict points there. So that's fine, and we have no residues. So this should actually be just 2 pi I times 0, which is 0. Okay. Now, what happens when we take the limit when I goes to positive infinity? Well, the limit when I goes to positive infinity of 0 is still just 0. And the limit here, when I goes to positive infinity, is going to be the same. Okay, it's just, sorry, I didn't mean to say that this limit is 0. But the limit when I goes to positive infinity of this integral, applying again Cauchy's residue theorem, we get that it is 0 again. Why? Because if we go from minus infinity to positive infinity, in all of this region, the function is still analytic. So again, this is 0. Meaning that, yes, that this equals to 0. And this is what we're looking for. We have the function, the integral we want to calculate, I, which is that integral, defined here, minus this integral, which we know how to calculate, is equal to 0. So, it's not too hard to see that I is equal to the integral from minus infinity to positive infinity of e to the minus x squared dx. Extremely well-known integral, extremely famous. This is just square root of pi. If you want to know how to do this integral, I will make videos about it, but the idea, just real quick, is just to consider I squared, which would be this, and then multiply by itself, but with a dummy variable here, which we'll call y, and we're going into going into 2 dimensions and passing to polar coordinates, we get an integral that's really easy to do and gives us square root of pi. But as I said, I will make a separate video just talking about this integral. So, I is the square root of pi. So, what's this? This is just, if you let me erase all of this, finally. Okay, just 1 minute, be patient. It's a lot to erase here. So, say. What we have is that so much chalk in there. The Fourier transform of e to the negative x squared is our normalization constant 1 over square root of 2 pi times this term we took out of the integral because it's constant in the x world, as black pen, red pen would say. Okay, and multiplied by I, which is that integral. And as we saw, using complex analysis, this integral I is just square root of pi. So, our final answer would be 1 over square root of 2, right, because the square root of pi just cancels out, e to the minus p squared over 4. And writing it nicely here, the Fourier transform of the Gaussian function e to the minus x squared is a function in the p world, in the momentum representation, which is equal to 1 over square root of 2 e to the minus p squared over 4. And what's curious about this? Well, as I said, we have gone from a function in the x world to a function in the p world. But what's curious about this function is that we started with a Gaussian function and we ended up with a Gaussian function. Of course, with a normal constant here and another constant multiplying the exponent, but in essence, it's just another Gaussian function. Well, it's just real nice. I will make videos talking about this and its relation to quantum physics. Just to give you a little taste, if we have our wave function, right? it might tell us that this is the wave function distribution of a particle within some point. This is the x-axis, and you see that here the particle actually has the biggest possibility of being right, because the area is the biggest possible. Not like, for example, in this region. In this region, the area is really little, so the probability of the particle being there is smaller. And really, this should not be e to the minus x squared, but rather e to the minus x squared, but this is just e to the minus 2 x squared, so in essence it's just another Gaussian function, okay? So it doesn't matter. Going to the momentum representation, you see that, well, this spreads out, and there's actually a lot of places where it could probably be, right, with a big probability. But on the momentum representation, Heisenberg's uncertainty principle tells us that, well, here the Gaussian function is going to have this shape. As you see, it is narrower and higher. This just means that the momentum, this is P, the momentum, is more localized. That is, there's more probability. That's the region where it's more probable to have a momentum is smaller. That is, it's more localized. It approaches a single value. But here, the particle could be anywhere with really large possibilities, right? It could be here, it could be here, it could be here, right? Any of these places. But here, it's more, of course, it could be anywhere again. It could have any momentum. But the probability is really great to have it in this small region here. Okay, this is just a really qualitative description, but just so you can see how Heisenberg's uncertainty principle holds in using Fourier transforms. In fact, well, this for a minimum wave packet, this becomes equal, as I said, and if the uncertainty in x is really big, that is, we don't know where the particle is, this goes to be real small, so that this evens out and gives us h bar over 2. Likewise, if we have a really big region in which we can find the particle with a lot of high probabilities, then the particle is going to be really localized. We want to be really sure about where it is. Not exactly, of course, but we want to have a really good idea where the particle is. And well, that's it for today. I hope you liked the video, and well, if you want more, just subscribe to the channel and I will keep uploading more videos. So see you in the next video.